This is this 3.35.3.3?
3.2.2.
I'm sorry, 3.2.2. And so there's a, they give you a plot, right? Get one more quickly. It starts at 120, and give me these first three frequencies. So this is 120 dB microvolts. So it's 120 dB microvolts right there. It's flat, and there's a break. It's in radians too, I believe. And mega this way, and it starts going down at minus 20 dB per decade here, and then there's a second break frequency, and it starts going down at 40 dB, right? And then over here, they have a gain that is linear. I mean, excuse me, it's going up to 20 dB per decade, right? And it starts at minus 30 dB. And it's going up at plus 20 dB per decade versus omega. And this is, I think, 10 to the 5th, isn't it?
Yes.
All right. And down here, where's the first break frequency on this one?
10 to the 6th.
All right, 10 to the 6th. And then this one?
20 to the 6th. Or 20 times 10 to the 6th.
And they want to know, so this is the input, right? Basically what he has here is a system where you have the amplification system that's represented by this. And then you have the input, which is represented by this. I'll call this just X, right here, X of, or X of omega, I should say. X of omega. And they want this output Y of omega, which is simply A times X of omega. Follow me on this, class? Basically, it's a simple input-output problem. This is the input. That's the amplifier, and they want the output. Now, this is how this stuff goes. What's the lowest frequency he shows? Is it 10 to the 5th?
He doesn't show anything there.
Okay. Well, here's what we can conclude. We'll go from 10 to the 5th up, because I think in his plot, he shows it 10 to the 5th, doesn't he?
Yeah, he wants the magnitude of the output at omega equals 50 times 10 to the 6th.
Just the output? We'll sketch the whole thing. We'll go from 10 to the 5th, 10 to the 5th, 10 to the 6th, or actually, yeah, and then 20 times 10 to the 6th. And pick it up from there. So, start out at 10 to the 5th, we're down here roughly. We have an input of 20 dB per decade. Y'all follow me on this? I mean, 20 dB microvolts. All right. But at that point, there's a minus 30 dB loss, you might say. It's a reduction in signal strength. So you start out here, your starting point is going to be 120 dB microvolts minus 30. And that means this starts right here at 90 dB microvolts. Now, the only thing I'm doing is I'm adding this to this. Y'all follow me in class? Now, it's going to keep, if you look at this is going up 20 dB per decade. So when I come to 10 to the 6th, I'm going to be 20 dB above that. Y'all follow me? This is the dB scale. That's 90 dB. I'll make it a little clearer. 90 dB. 90 dB or microvolts. And it's coming in at 90, and it's going to go up at 20 dB per decade until we hit 10 to the 6th, And at 10 to the 6 right there, it's gonna be up by 20 dB, so it's gonna be 90 plus 20, where this is gonna be 110 dB microvolts right here. That would be this one. Then, if you look here, now this is coming down by 20 dB per decade. Y'all follow me at that point? So if this is going up at 20, but that's coming down, the net effect is it's flat. Y'all follow me on that? It's just gonna be flat. It's gonna stay there. Then when we hit 20 times 10 to the 6, and this is in the omega domain, now it starts falling down 40 dB. So now it's gonna start decreasing at a rate of 20 dB per decade, because the net effect is you got minus 40 going down, plus 20 going up, it's minus 20 going down. So at this point, it starts coming down at minus 20 dB per decade. And they wanted it at 50, is that it?
Yes, 50 times 10 to the 6.
Okay, so at 50, here's how you get it. Now, last time I told you about this, we know the value right here, 20 times 10 to the 6, right? Y'all follow? We know that value, that's 110. So to get the value here, we're gonna take the 110 dB microvolts, and then you're gonna take minus 20 times the log of the difference in the frequency you want. This is the point you're gonna start here, and that's the 110. And we have to figure out the reduction here, so it's minus 20, because that's how many dB that you're gonna lose per decade. It's the log of the upper frequency, which is 50 times 10 to the 6, divided by the lower frequency that you started at, which is 20. And can you give me that value?
Uh, 102.04.
That would be dB microvolts. Is that the agreement? But this is one of the things, I don't know how much you learn in signals and systems about this, but whenever you're doing plots that have either increases or decreases, that's 20, 40, 60 dB, and you're in the frequency domain, because all this is done, it's a logarithmic scale. You're simply adding the effects of this and this, of the input times the amplifier, and you'll get that. Y'all with me? Everybody, I mean, it's.
How come you use the logs of 50 over 20 to?
This actual this scale right here is 20 times the log of the actual voltage divided by 10 to the minus 6, right? That's dB microvolts on that scale. That means it's gonna be logarithmically varying on this scale.
Yeah.
This is also gonna be a log scale there. And whenever you want the difference,
Yeah.
we could go through the math on this
Yeah.
in detail.
I think I got
Between
it.
2 points. Like if it was exactly 1 decade, then it would be minus 20 times the log of 10, right? Because the upper frequency would be 10 times the lower frequency you started at. Y'all follow?
Mhm.
Log of 10 is 1, would be exactly 20 dB.
Yeah.
If you went 2 decades, then it would be 40 dB. If you had 100 divided by 100, a factor of 100 there, log of 100 is 2, then you have minus 40. So it's a logarithmically decreasing and increasing scale. And that's
So when you got actually full decades that you're going, you don't need to use the log
No,
in the
that's right.
equation. But
I mean-
necessarily, because you can.
That's what I did right here. When I went from this point to this point, this is 10 to the 5th, this is 10 to the 6th, so I
Yeah.
could easily figure out, if I go from there to there, I'm dropping exactly 20, or I'm sorry, increasing exactly 20 dB
Yeah.
per decade.
Mhm.
But this last part, I have to interpolate that.
Okay.
All right, another one, might as well do a few more. Let me get this. What I'm showing you is, this is basically real EMC engineering and the way you have to go about analyzing systems. So this starts at 100 dB microvolts, right?
That's the, I think that's the second.
Did I miss that?
I think it's that. But
Okay, all right, and that is at 10 to the fifth, right? We can just start there.
okay.
So this is omega, and this is be 10 to the fifth here. And it's gonna go up at a rate of 20, right?
Yes.
Plus 20 dB per decade. Then it's gonna hit a peak value here at
10 to the sixth
10 to the sixth, nice of them. Then it's gonna come down to 20 dB?
at 40.
40, sorry. So now it's coming down rapidly. Minus 40 dB per decade. Go ahead.
And then it gives between there's 2 meganon and 3 meganon. And then there's the circuit.
All right, well that just gives me a reference. All right, and that circuit is 1K, 400 gigahertz. Huh? So then they have a circuit. And they have a resistor R, and R is 1,000 ohms. And it goes in parallel into a parallel combination of a capacitance parallel with the resistance, same resistance value. And what they want is this. They're looking for V out in dB microvolts, right? So can you read that problem just entirely?
A periodic waveform with a meganon equals 10 to the fifth radians per second is applied to a circuit as shown in the figure to determine the level of the 50th harmonic.
All right, so in essence, what they're asking for, they give you the actual spectrum of the inputs. So these are basically just straight lines that sum, that this would be 2 omega naught, 3 omega naught, and so forth. But these are the harmonic frequencies. The fundamental is 10 to the fifth, I think they say. All right, so then it would be 10 to the fifth, 2 times 10 to the fifth, 3 times 10 to the fifth, and so forth. They want it at the 50th harmonic?
Yes.
All right, so this is the actual, this is omega naught. 50 times that's 50 times 10 to the fifth, or 5 times 10 to the sixth, right? So they want it out here at 5 times 10 to the sixth. This is the frequency. They want the output of the circuit. So first thing we have to do is find out what the input value is right there. Do y'all follow me? This is the spectrum, and we have to find out what this value is at that frequency, because that value is going to correspond in dB microvolts to that value. Are you with me, class? Then we'll put on the filter and see what happens. So for this one, if you just take a look at this, from 10 to the fifth to 10 to the sixth, I'm increasing at 20 dB per decade. So my value would be, when I'm looking at from V source in dB microvolts, and I want it at 5 times 10 to the sixth, first I start at 100 dB microvolts. We'll assume the units are dB microvolts. From here to here, it's exactly 1 decade, so it goes up by 20. Now I've got the value here, and then from here to 5 times 10 to the sixth, it's going down at 40 dB per decade, right? But I can't just say 40. What I have to do is say it's minus 40, right? And it's times the log of the upper frequency I stopped at, which is 5 times 10 to the sixth, over the lower frequency I started at, which is 10 to the sixth, or log of 5. Now, can you give me that value? Yeah.
How come you don't use the log for the plus 20 TVs?
Well, I see it's exactly a decade, right? I could put plus 20 times log of 10 to the sixth over 10 to the fifth, but log of 10 is 1. So it's exactly 20. That's the reason I didn't do that. They're all good questions.
92.04.
dB microvolts. All right, now we take a look and write equations for the output of this filter. Are you with me, everybody, on this one? So when we take a look at this filter, we could say, really, there's a parallel impedance here. I'll call it ZRC here. And that would be 1 over, really 1 over R plus J omega C. Does everybody understand how I'm getting that? I'm taking, anytime you have impedances in parallel, if you want the value, take 1 over the first impedance plus 1 over the second impedance. Some people take first impedance times second impedance over first impedance plus second impedance. This one, as it turns out, it's probably gonna be a little easier to do it this way. So now I take a look at this right here, and I multiply top and bottom by R, and I get this. It's simply R over 1 plus J omega R times C. Does everybody follow me on this? Class, you guys got that? Okay, that's just a parallel combination of that. Then when I look at my V out over V in, or my V source, let's say V source, I take the output impedance right there, which is going to be simply ZRC, and I divide it by ZRC plus R. I'm just showing you, that's just the transfer function, right? Output over input is really 2 series of impedances, right? Everybody okay with that? You're not asking a question. So then I divide top and bottom by ZRC, and I get 1 over 1 plus R over ZRC. Now this is the important part. This makes things simple, doing it this way. And then after that, I'm going to go ahead and put in the values for ZRC. So I have 1 over 1 plus R divided by ZRC. Well, this is ZRC, so if I divide by that, I flip the thing. And that's going to be equal to 1 plus J omega RC divided by R. Take a look at that, make sure you agree with me. Y'all follow me on this one? All right. Now, at that point, you see the R's canceled, don't you? That R and this R cancels, then I get 1 plus 1 plus J omega RC, or I have 1 over 2 plus J omega RC. And that's the transfer function. You can call it H of omega if you want. You all agree with this, class? All right, now, next step, I want V out, so V out, this would be linear now, is equal to the H, the transfer function of omega times Vs. And now I put everything in dB microvolts, because the input was given in dB microvolts. So now I take 20 times the log of V out over 10 to the minus 6 is equal to 20 times the log of Vs over 10 to the minus 6, or plus 20 times the log of simply the magnitude of H of omega. And here what I'm doing is when you take log of A times B, just for everyone, so we know. When you have log of A times B, that's the log of A plus the log of B. Y'all follow me? I want to make sure you understand why that second part just is an additive term. We have this. That's right here. Follow me? That's the input, and this is the value. So we have the value of this. Now we need to get the value of this. Agreed? And it has to be at 5 times 10 to the 6th. All right, so now I come over here, and first I get my H from them. I'm going to get the H function. I want to get the transfer function's magnitude. So that's going to be 1 over, and I have to take the square root. I have to square this and square that, just to make up RC. So it's going to be 4 plus, and then it's going to be omega, in this case, it's going to be 5 times 10 to the 6th. And R was one case, so that's going to be simply times 10 to the 3rd. And then C is, I don't even think I put C down here, but what is C for this one?
400 picofarads.
So C is really 4 times 10 to the minus 10. And all this has to be squared down there. So if you can give me the magnitude of that, if you don't mind. Let's see here. That's 10 to the 9 times 10 to the minus 10. That's 10 to the minus 1. That's 20 times 10 to the minus 1 is 2. So it's 2 squared is 4, 4, 8. So this is 1 over square root of 8, I think. You check me on that one.
Yeah, 353. Which is, yeah,
0.353? Okay.
Yes.
Now you come over here and we can write the calculation down. That means the output of this circuit at 50, or at 5 mega radians per second would be equal to 92.04. And then it's gonna be plus, it's gonna be a negative value, 20 times the log of the magnitude of, and that's 0.53, or 0.353, 0.353. And what's that value?
82.99. Which is basically like
EV microvolts. And what is it again?
83.01.
Alright, so, y'all follow how to do that calculation? The key is when you're doing everything in dB, you always try to get the back, this is my opinion, try to make this transfer function as easy to deal with and calculate as possible. Don't make it complicated. Any questions? That's a good problem. That really kind of makes you think about everything in the frequency domain in terms of dB microvolts. Another one? Might as well. This one, you don't even need to show the actual waveform of the circuit.
Real quick, what is H of omega stand for? Is it?
The transfer function right here.
Transfer, okay.
Does this making sense to everybody? Are we good? Okay.
Can you believe that part real quick? I'm just gonna take a picture.
What's it?
Can you take
Yeah,
a picture of that?
go ahead. I don't know if anybody else comes down Sanford to get here, but it's blocked off. You can't drive down. And a few other things happen somewhere. An interesting
doing a lot.
delays. By the way, he's recording this in case, and you posted a link. So if you want to, you can look at the actual video recording. All right, so let me draw this circuit. We'll put the values in 1 second. Resistor R, I think it's the same kind of circuit, isn't it? R in parallel with C?
The resistor in that circuit, but I guess.
Oh, they're in parallel, doesn't matter.
Yeah.
That's that. And, so this is R, and all the R's are 1 kilo.
Yes.
And then this is C, and C is
That's what you're finding.
question mark. And this is BS. Any information about BS?
It's a 5-volt, 10 megahertz oscillator.
So this is 5 volt peak, and the frequency and this is like clock. The frequency is equal to
10 megahertz.
10 megahertz.
Yeah.
So that's 10 to the 7 hertz. And the duty cycle
50%.
is 50%. which isn't even gonna come to play a role in this one. Now, I'll show you why. So, when I take a look at this, remember, just like last time, I made an impedance here. I called it ZRC, right? All right, ZRC. Or call it ZRC. Is going to be equal to 1 over R plus J omega C. I want to just make sure you see this a couple of times. Then I multiply top and bottom by R, so I get R over 1 plus J omega R times C. And then to get this output voltage right here, which I call a transfer function, V out over V in, or V source, that's equal to my H omega, and that's equal to ZRC divided by ZRC plus R. Y'all agree with that plus? Same as before. Follow me? It's just a simple, it's a voltage division of sorts, isn't it? That's all it is. Then I divide by ZRC and I get 1 over 1 plus R over ZRC. I'm just simplifying, going through it. Same thing I did last problem. And I see this one is going to be 1 over 1 plus R, and then it's going to be divided by R, right? And it's times 1 plus J omega R times C. And again, when I take this and I take 1 over it, then the R goes to the bottom, and 1 plus J omega RC comes to the top. And I'm left with this 1 over 2 plus J omega R times C. Everybody with me at that point? Just getting the transfer function. Now that I have that transfer function, I come down here, and they want the level of the fifth harmonic to be, or was it fifth?
Yeah.
To be 1/20th of the,
Reduced by 20 dB.
or 20, oh, sorry, 20 dB. All right, so now we start out with what the impedance of this would be, or the only thing we need to do is, you see this right here? This is gonna have a value. We wanna have the fifth harmonic to be down by 20 dB, all right? Or by a factor of, if you think about it, 10, isn't that right? Every time, you know, I'll spend more time in a second on this. So first, we find the level at omega naught. So the actual value of H at omega naught, which is the 10 to the 7th hertz, that's simply equal to 1 over 2 plus, and this would be J times just omega naught. I'll leave it as omega naught times R times C. Or it's equal to 1 over square root of 4 plus omega naught times R times C squared. That's the level at omega naught, and the level at 5 omega naught, that's the fifth harmonic, is going to be 1 over 2 plus, and really, I should go back into this, 1 over 2 plus J times 5 omega naught R times C. And the magnitude of this is going to be 1 over square root of 4 plus, and it's going to be 5 omega naught R times C squared. Just show you this. So, and when you think about a reduction in dB, if you're talking about voltage, anything in dB, called dB microvolts, is really 20 times the log of whatever it is. In this case, it's going to be H. So if we want to be down by 20 dB, that means 20 times the log of H has to be, I mean, minus 20 dB has to be equal to times 20 times the log of the H functions. And it's really the ratio, I should say. the ratio of H at 5 omega naught over H at omega naught, and it's the magnitude. Can you follow me on this, class? He wants this to be down minus 20 dB. Just catch me on this, everyone? And it's a ratio. Now, I can get rid of the 20, so now I have minus 1 is equal to the log of H of 5 omega naught over H of omega naught. Then 10 to those powers, well, 10 to the minus 1 is simply 1/10 is equal to H of 5 omega naught over H of omega naught. Y'all see the reasoning here? So that means the output at 5 omega naught has to be 1/10 the output at omega naught. That's as simple as it gets. Follow me, class? We have the value of R. So over here, if I take a look at this, I'm gonna try to do it this way. So I have to take this value and divide it by 10. So I have 1/10 of 1 over the square root of 4 plus omega naught RC squared is equal to 1 over the square root of 4 plus, and this is 5 omega naught R times C squared. Can y'all follow what's been on here? Just give it a second. I'm saying the input at omega naught is, the ratio, the transfer function is right there. At 5 omega naught, right here, it has to be 1/10 this value. So that's how I came to terms of that equation. Take a good look and think about what I'm doing. With me? Gotta make sure you are. Okay. Now, at this point, it's up to you how you want to do it. I'm just going to suggest something. First thing, I'd flip it. I would do a 1 over everything because it's equal. And so I have 10 here times square root of 4 plus omega naught RC squared equal square root of 4 plus 5 omega naught R times C squared. Right. Everybody agree with that? I just took 1 over both sides. Still, it's no violation of the equal sign. It's not inequality. Now, I'll square both sides. Y'all follow me? Squaring both sides gives this the value of 100 here. Matter of fact, let me write it up here. So when I square both sides, I'm going to get, this is going to become 100 in a second. I'll leave it as 10 there. So I get 100 times 4 plus, and it's going to be omega naught RC squared is equal to 4 plus 5 omega naught RC squared. Everybody give me that? All right. Then I'll multiply through, so I get, I'll do it right here. I get 400 plus 400 omega naught R times C squared.
100. It should be 100 omega naught.
I'm sorry, 100, you're right. 100 times that equal to 4 plus, and this is gonna be 25 times omega naught R times C squared. With me on that one? Now, I'm solving for omega naught RC. That's what I'm running. So you can see that. So now, probably the easiest way to do this is, wait a second, did I do something wrong? Well, you know what? We're trying to go down 20 dB in simply, factor of 5, not 10. That's an impossibility. We're gonna get, this is, I think I know what he meant by the problem statement, but this is an impossible. You're gonna get a negative value for this. If you take a look at this, here's what's gonna happen. If I take the 4 on this side, I get 400 minus 4 on this side. Then, if I take the 100 on that side, I'm gonna get a minus 75, making out RC squared. That's an impossible value. What? You can't solve that and get a meaningful answer. But read that problem again.
A 5-volt, 10 megahertz oscillator having a rise fall time of 10 nanoseconds and 50% duty cycle is applied to a gate as shown in the figure. Determine the value of the capacitance such that the fifth harmonic is reduced by 20 dB in the gate voltage.
So what he really wants is the value of that transfer function to be 1/10. All right, here's what he's saying in this one. He's not actually taking the value. He's not taking the value of the circuit operating at omega naught and then saying it has to be reduced at the output of the fifth harmonic by 20 dB. It's an impossibility. You can only get 20 dB per decade. You would have to have at least a decade to do that. What he's really saying is he wants the value of the transfer function of H at 5 omega naught to be equal to 1/10. That's 20 dB. That's ultimately what he's saying. So if you look at this, he didn't state it that way. This was equal to just the transfer function itself at 5 omega naught. Well, that's simply 1 over 2 plus, and this is going to be J times 5 omega naught R times C. That would be the transfer function. He wants the magnitude of that to be 1/10, and this is doable. So now I have 1 over 10 equal to 1 over the square root of 4 plus, and then it's going to be 5 omega naught R times C squared. Now I go ahead and invert this, so I have 10 equal to square root of 4 plus 5 omega naught R times C squared. The only thing I'm doing is taking the transfer function and I'm evaluating 5 omega naught and I'm setting it equal to 1/10. That's what he's really talking about. And if you take a look at this, I'll square this, I get 100, and that would be equal to 4 plus 5, well, that'd be 25 times omega naught RC, actually, I'll just do it, leave the 5 in there. So that's equal to 5 omega naught R times C squared. Then I'll take 4 on this side, so I have 100 minus 4 is equal to 5 omega naught RC squared. And, I mean, at this point, pick the square root of both sides, so I have square root of 100 minus 4, which is 96. 96, and then divided by 5 omega naught, and that's times 2 pi times F minus 10 to the 7. This 10 to the 7 hertz was the actual 10 megahertz was the frequency, and then R was 1,000, right?
Yes.
And that should be C. You can give that to me.
Uh, 195.96 picofarads.
Is that what you got?
He has 63.34.
Did we do something wrong with the calculation?
Oh, I don't have 2 pi.
What's that?
I forgot to put 2 pi for omega.
We're supposed to square the 5.
Pardon?
We're supposed to square the 5.
What I try to do is, if I take this right here and take the square root of it, right? Then I get this, right?
Okay.
And then if you divide by 5 omega naught RC, 5 omega naught R, you should get the value. So that's 96 over 5. Omega naught is 2 pi times 10 to the 7th, right? R is 1,000, isn't it? Check that. I think this is the right calculation. Did you get? Pardon me?
R is 1,000, but
What do you get for C? You said 31?
I read the same thing, 31.19.
yeah.
That's the right calculation. Unless I saw something in my glasses. This guy's doing. Oh, yeah. Here's what he's actually saying. Just bear with me, let me finish this. What he doesn't do is show the circuit he's talking about and the voltages, and then how it should adapt it. Here's what he's saying. He's got this sort of plus and minus Vs. He's got a resistor R here and R here. The output voltage here for any harmonic without the capacitor is simply going to be plus and minus 1/2 Vs. Y'all follow? It's a simple. He wants that reduced by 20 dB. So he wants 1/2 Vs reduced by, that's a factor of 20. Y'all follow me? If you reduce whatever you're reducing by 20 dB, it goes down to exactly 1/10 of that value. This is already 1/2 that, right? So what he wants is the transfer function. This will nail it. At 5 omega naught to be equal to simply 1 over 20. So it's the same thing we did before. And I apologize, but what he should do, have this circuit just show the voltage output. Then say you want this voltage reduced by 20 dB, the output voltage at the actual frequency, which is 5 omega naught, by adding a capacitor here. So then you add this capacitor and figure out what the value is. That's the problem statement. But it's not apparent when he said this. There's different ways you can interpret it. First, the capacitor was there in the beginning, and you want to find out what that value should be, so you get 20 dB reduction when you increase by on the fifth harmonic. That's an impossibility. You can only drop 20 dB per decade for any RC circuit. So when he does that, this one we're going to get in a second. Well, that's equal to 1 over, and here it's going to be 2 plus J 5 omega naught R times C. So now I'm going to go ahead and get the magnitude of this. So I have 1 over 20 equal to 1 over square root of 4 plus, and this is going to be 5 omega naught R times C squared. I'll flip it. Now I have 20 equal to square root of 4 plus 5 omega naught R times C squared. Y'all follow me? I'm doing the same thing I did before. Now I square both sides and I get 400 on this side is equal to 4 plus 5 omega naught RC squared. Subtract 4 from 400, that's 396, so I have 396 on this side. I take the square root of that, and I divide by 5 times 2 pi times 10 to the 7th times R, which is 10 to the 3rd, and that should be the value of C. I'm just solving for C in that equation. Is that right?
Mm-hmm.
Did you do it?
Yeah.
All right, 63.1?
3, 4.
You can figure. Now, I won't give you a problem that you can misinterpret. what I'll say is I want a certain output voltage level at the fifth harmonic or something. I wouldn't give you anything that could be misinterpreted the way I misinterpreted that. I'm sorry. You want one more? I don't. Which one did you want?
This one's the last one.
This one?
Yes.
All right, so let me just do this. This problem is a wordy problem. And the capacitor in a lot of these problems that he has, they really represent the gate capacitance of an FET. And because this is about the values you get. So, last problem, go ahead. What's the number?
A 10 megahertz clock oscillator having a 10 ohm internal resistance.
This is 10 megahertz.
Yes.
And it's got, do this, so this is my oscillator. And it's got a resistance of 10 ohms?
Yes.
Okay.
An open circuit voltage waveform as a trapezoidal pulse train with a 50% duty cycle. And rise and fall times of 2 nanoseconds.
T rise equal to tau fall, 2 nanoseconds, go ahead.
Determine the value of a capacitor that when placed across the oscillator output will reduce the output voltage of the fifth harmonic by 10 dB.
All right, well, I mean, do they have any other resistors? Well, it's just a word problem. All right. There's nothing, all right.
Yeah, that's it.
Okay, so first, what does he give us VS? Peak value, 5 volts?
What does it say?
All right, well, we actually don't need it, but it's kind of nice. We could make it 5 volts, but here's the deal with this one. If you look, he's saying if we have a standard input waveform that looks like this, it's this type of repetitive waveform. It's a clock, basically. And this is the period T. This is tau. And this is tau rise. And this would be tau fall with here. I'm just showing you something I did before. And this is the level A, right? Follow me on this, class? This would be VS, so it's repetitive waveform. What that will look like when we actually do the spectrum, the envelope of what we care about, the worst case values. It'll be flat here, and this value is going to be 20 times the log right here and the duty cycle is 50%, right?
Yes.
So normally it's 2A times the duty cycle, because duty cycle is 50% or 1/2, it's just going to be equal to A over 10 to the minus 6, where A is the magnitude of the signal, and that would be in dB microvolts. The first break frequency here is 1 over pi times tau. We'll get to that in a second. Keeps coming down. The second break frequency is going to be 1 over pi tau rise. And then it goes from 20 dB per decade to minus 40 dB per decade. It's important to appreciate what that waveform looks like. With me, class? All right, we'll get the values for that. And so, because F naught is 10 megahertz, I know the period is equal to 1 over 10 megahertz, or 10 to the 7th, so it's 10 to the minus 7 seconds. Does everybody understand how I got that? If the fundamental frequency is given, just 1 over that is the period of the waveform. After that, I can get tau, and tau is really the duty cycle, or in this case, it's 50% or 1/2 times t. So that means my value, the value of tau is going to be 1/2 this, or it's 5 times 10 to the minus 8 seconds. With me on this? He gives us t rise, tau rises 2 nanoseconds, is that right?
Yes.
That's fast. All right. So when we come down here, you can tell me what that frequency is. It's 1/pi times 5 times 10 to the minus 8. 5 megahertz, something like that.
6.37 megahertz.
6.37 megahertz. And for this one, tau rise is only 2 nanoseconds. That's up there. 33, something like that. Megahertz.
0.159 gigahertz. Or 159 megahertz.
Yeah, I like that better. 159 megahertz. Right. Okay. So after that, we're going to find signal strength at the frequency of interest. And he said, where does he want this output reduced at what frequency?
Fifth harmonic by 10 dB.
All right. So now it comes down to this. When you talk about a 10 dB reduction, so if you have minus 10 dB, we're talking about voltages here, that's equal to 20 times the log. This is what the output would be reduced by. We have to find out how much it is. Log of the actual H value. This is the transfer function we'll calculate. So that's minus 1/2 is equal to log of H. And that's going to be 10 to the minus 1/2. And that's what H is. So can you tell me what that is? 1 over the square root of 10. What, about 0.3 something?
0.316.
0.316. That's the level of reduction. Whatever we find it is, we have to reduce it by that much. You all follow me? We want, the capacitor has to reduce it by that much. So if I take a look at this, and I want the value of the fifth harmonic, right? So this is a 10 megahertz, so 10 meg would be right here. 10 megahertz. And we have this, the fifth harmonic would be, wait a second.
The next part of the question is, given that the open circuit voltage transitions from 0 to 5, estimate the level of this fifth harmonic. That seems like a
So he's just saying this is 5 volts, A is 5 volts. We can actually, if that's 5 volts, I think this is 133. If you just check this, this would make this. If A equals 5, that makes this level about 133 dB microvolts, if I'm not mistaken.
133.98.
All right. So the fifth harmonic would be at 50 megahertz, right? Let's get the signal strength. Might as well do this the whole way. So this is where we come in at. Here's the first break frequency, and we want the value of this signal at 50 megahertz. You'll notice that the second cut frequency is at 159. It's way, way up there. So we're only on this part of the curve. Follow me on this, guys? So I need to find the level right here, and that's at 50 megahertz of the actual signal. This would be the open circuit voltage as dB waveform. So that value would be what? Well, it would be, I'd say V and dB microvolts of the fifth harmonic. So this is And this is the source too. So I got 133.98. Then I have minus 20. Now I go from here to 50. So I go start at 6.37. Lower one is going to be 6.37 megahertz, and I stop at 50 megahertz. So the upper one's 50. So can you give me that level right there?
116.08.
By the way, since he wants that level reduced by 10 dB, the signal, the last part of the problem, he says, well, what would the output voltage be? Estimate the output voltage, just subtract 10 from that, and it's 106, so the V out, and this is an estimate with the capacitor would just be 116.08 minus 10, or 106.8 dB microvolts. Does he have that there? So that's straightforward. Now to get the value of the capacitor that will do that, these are the kind of problems you like, because it's a simple RC circuit, and you want the value of the output voltage to be 316 at the fifth harmonic, right? So I'll do it right here. The transfer function of this right here, V out over V in, or V source, if you will. That's simply going to be the impedance of the capacitor, which is 1 over J omega C over 1 over J omega C plus R. Do you all agree with that, class? Take the impedance of, this is a simple series impedance circuit, so it's voltage division. And if I want V out over Vs, that would be it. Does everybody agree with that? All right. Now, I take that, I'm going to modify it to make it easy on myself, multiply everything by J omega C. I have 1 over 1 plus J omega R times C. This is going to be my V out, or just call it H. You agree with that? Now, that magnitude at the fifth harmonic has to be equal to 0.316, right? So now I take 0.316 equal to, the magnitude of this is 1 over the square root of 1 plus, and this is going to be fifth harmonic would be 5 omega naught times RC squared. And then I have to take 1 over that business. So when I take 1 over this, I get 1 plus 5 omega naught R times C squared is equal to 1 over 0.316. And then I can take 1 to the other side, so I have 1 over 0.316 minus 1. And then I can take the square root of that, whatever that value is, and divide that by 5 times omega naught, which is 2 pi times F, and it was 10 megahertz, or so it's times 10 to the 7 times R. Is R 1,000 in this one?
It's 10.
10, I'm sorry, 10. And that should be the value of C. So, and really, once you're here, you're just solving for C. That's the ticket right there. But is that the fifth harmonic?
955 picofarads.
Is that what you got?
Yeah.
And what I'm doing with these problems is I'm trying to expose you to the way, most of the time they do EMC problems and really high frequency problems, frequency design problems. It's always in dB microvolts, and you're always looking at really the envelopes of things for worst case behavior. Any questions about that? Try to remember when you talk about dB reduction, if you want a linear value of that, if it's voltage or current, it's 20 times the log of the transfer function. If it's power, it's 10 times the log. So that's the big thing that people tend to make mistakes. This might seem a little confusing, but if you go through what we just did, measure clicks, and you'll see it. All right. Now, any other questions? One more thing I was going to go through today, and I got a few minutes, and that is going to be common mode shows. This is in his book, and I'll give you the page. You're going to see there's not much to this. He really calls them ferrite shows. So this is on page 538. He has a section on filters too, but you got, I think you had your basic high pass, low pass, band pass filters in circuits. You guys know what Chebyshev and Butterworth filters are? Are you familiar with those terms or not? You are? Where did you get them? What class did you do?
I heard about it at work, so.
Oh, okay. I'm always interested in where certain things are brought up. Chebyshev and Butterworth filters are, well, typically they're used with active circuits because you get a much, usually you have an amplifier involved. But you will be exposed to that probably. Have you had your analog electronics class yet? You have? If you've had it, didn't you have anything with Butterworth filters?
We didn't talk about Butterworth first.
Or Chebyshev?
I'm familiar with choke, but I assume that it's the same idea as like RF choke in your amplifiers.
Well, the filtering is a little different. It's a much higher order, but let me get back to this thing and finish this joke. So this is a choke. It's a common mode choke. Common mode filter. Just call it common mode filter. And really it's called a choke. So here's what they are in a nutshell. And I made them. You may make them too. You take a simple donut-shaped ferrite. It's going to be some kind of a ferrite material. It means mu relative is much, much greater than 1. Much like 1,000 to 2,000. And now we run wire around this thing. We're going to have N turns here. It's going to create an inductor. And then you come down here with a second wire, because this is going to be put in line with any kind of a cable, the differential cable, where you're driving it with a differential signal. And I'll call this I1 and this I2. And there's some load over here, but it doesn't even matter. So the reason we use these is we're trying to stop what are called common mode currents and allow differential mode currents to pass. Now with the normal system, when I say differential current or differential anything, if you think of any system, communication, doesn't matter, power, you have a source voltage, you're going to have some load, and the circuit current flows this way. So the current above, this is a very long, thin line. The current here, same magnitude, but opposite direction as the current here. That's what you want. You want that to work that way. What you don't want is the current to go that way in both of them. That's called a common mode current. Have you heard that term before? Common mode currents are horrible for a lot of reasons, but they're caused by all sorts of things. You could have induced magnetic fields inducing current causing the same current to go in both wires. You can have something like lightning striking something, and then the currents will try to run in parallel on the wire, but they'll also, in doing so, they'll damage all your electronics. So they try to eliminate that. And this is how come we eliminate them by adding this. Now, without getting into everything, do you remember how many have had Dr. Gross? All right, Dr. Gross does a thing. He takes a straight bar and he winds a coil of wire on it. He says, take your fingers on your right hand, put it in the direction current flowing in those coils, and your thumb points in the direction of flux. Do you all remember that? And you would dot the coil side, right? You would dot one side. Then you take a look at your second coil, if it's a transformer, and if you assume a dot and put current in there, goes around, you take your right hand and let your fingers in your right hand wrap in the direction of current. Your thumb points in the direction. If it's the same direction as the primary, then you put the dot on that terminal. If not, you reverse it. Do you remember that lecture? Right. So I'm not even going to do that. I'm just going to put the dot there. We're assuming that means that. Okay. So now you have basically a transformer you've created, and the transformer has primary L and it has mutual L. Y'all follow? So that whole thing becomes this. It's simply going to be represented electrically as a primary inductance, just L, with a dot there. Dot here with another primary, and there's going to be a mutual inductance here. Here's current I1, here's current I2. Y'all follow? And what we're going to do is pretty simple. We're going to find out what the voltage is right here and what the voltage is right here from this circuit. Now you remember these are actually mutually coupled circuits. They're not pure transformers. A transformer is usually assume the coupling coefficient is almost perfect. And they don't even talk about any, they use the turns ratio. You all remember that? Turns ratio to calculate things that you never use the actual, typically you don't, inductances and things like that. So for this type of a circuit, V1 looks like, in terms of its output, it would be J omega L, we're assuming L's are the same, times I1, plus, and because of the way the dot is, J omega M times I2. In like manner, V2 would be equal to J omega, and then would be M I1 plus J omega L I2. And the only thing I've done there, I've gone to the frequency domain and I've expressed the primary and secondary voltages in terms of the currents. That's it. Now, here's the deal when you talk about common mode shocks. If we talk about common mode currents, that means I1 is equal to I2, it's called I common. Are you with me, class? If the currents, if you're looking at this thing, you want to see actual voltage develop when the currents are in the same direction. You do this. And you find out when you have common mode currents, I'll put it up here and get out of the way. Your V1 will be equal to J omega L I common plus J omega M I common, or V1 is equal to simply J omega times L plus M I common. Can you all follow me on that? You're assuming common mode. You want to find out what voltage is developed across that primary, and that's what it is. Now, if you look at this, what is the impedance of the primary? If I take V1 divided by I common, that would be Z common right here. And I mean, it would be Z of the actual primary, Z1. And that's just equal to J omega L plus M. So here's the takeaway for this. When you have a common mode, it would be the same, by the way, Z1 would be the same thing as Z2, the impedance of that coil. When you have common mode currents flowing, and I'll put it here, when you have common mode currents, then effectively the impedance of the top winding looks like J omega L plus M, and the impedance of the bottom winding looks like J omega L plus M. So the net effect is the impedance that would be stopping common mode currents would be this plus this, but notice I broke them down, I showed it right there, that's the impedance on this side, that's the impedance on this side. It's being added. You'll notice it's adding the effects of the mutual. Everybody with me on that? Let me finish my thought here with differential. Now, if you come over and you take a look at differential currents, and that's what you want to allow to flow, differential currents. That's I1 is equal to minus I2, or it's really equal to I differential. In other words, when we have differential currents, we're going to have, this is the top and this is the bottom, we're going to have I differential flowing this way and the same magnitude opposite I differential in this direction. And y'all with me on this, class? You're going to have same magnitude, opposite direction. That's what you want to get through. You want no impedance at all for this. Well, that's still V1, and that's still V2. So when you look at this, now when we put down the equation, V1 is equal to J omega L times I differential. But here, because the second current is now in the opposite direction, it's negative that. Now this becomes minus J omega M times I differential. By the same token, V2 will have, here it's going to be minus J omega M times I differential, and then plus J omega L times I differential. So V1 will have the same exact form as V2, are really J omega, but here L minus M is the impedance. Do y'all follow me? Now typically when you wind those, when you actually do a ferrite core like this, the way I'm showing you, the mutual and the self are almost identical, which means this term is about zero, so it has no real effect on the actual stopping current or voltage from going the way you want it to. Do y'all follow me? Because that's what you want, this impedance, you want V1 to be zero. Or if you look at the impedance, if you take V1 over, it's times I differential, pardon me, well, times I differential, that's just J omega L minus M. So when you have differential currents, this is L minus M. And that will allow that to pass, but it'll stop common mode currents. And that's the whole game with these chokers. I'll give you one or two problems on this. And for Friday, we'll have a quiz. The quiz will be on the EMC business, those problems we just did today earlier. But I will give you some more information about this, and we'll be starting at the last chapter too. That's going to be really microwave. Now we have the next week and then a Monday, right? So we have 4 class periods, and then we'll get through the microwave without any problem. Microwave section, all right? If you need to see me, upstairs. If y'all follow me on this one, this stuff really is not bad at all. When it was spoken, he doesn't do any of the, he doesn't go through much of anything. He just says, here it is. It's ferrite chokes in these case 537. Okay? How many people are missing? 2, 4, 6, 8, 10, 12. Not bad. We're missing a couple. Did you understand today? You're gonna have to go through that stuff.
This is kind of reminds me of the golf system. Yeah.